Hi everyone. In today's video, in the topic of advanced ship stability, I will take up a new question on bilging of end compartments. This is example number 2. If you haven't watched example 1, the link is in the description section below. This example is different from the previous example because this will also discuss the concept of permeability. Another thing is that I have pre-written the solution so that we don't waste too much time in me writing. I will try to explain the solution. I will also explain some concepts which I may have not explained in my previous example so that you have a better understanding of this topic. So without much ado, let's get into this question. The question says there is a box shaped vessel which is 150 meters long and 20 meters wide. It is floating at an even keel draft of 7 meters, that is the forward and aft draft is same, and it is floating in seawater, that is the density is 1.025. We know that now. The forwardmost compartment on this vessel was filled with cargo with a permeability of 25. I will explain what permeability is as we go along. And the compartment was 15 meters long and 20 meters wide, and it gets bilged. That means water starts to come into this compartment. You have to find the new drafts forward and aft. All right, so let's get started. So I will show you how to draw the diagram, but I have pre-written the solution as you can see below, and I will explain as we go along, so that is better. Otherwise, if I'm writing along with you, then it becomes a bit long. All right, so let's draw the diagram. You must always draw diagrams. So let's draw a box shaped vessel. Very simple, a box shaped vessel which is a rectangle. All right, so my drawings are anyway not very great, but you can draw maybe much better than I do. All right, so I've got a box shaped vessel here. The length of this compartment is 150 meters. I will have to draw two of these diagrams. I'll tell you why later on. So this is 150 meters is the length of the compartment, and the breadth or the width I cannot show. This is not a three-dimensional diagram, so I will draw something like this, and this becomes 20 meters, which is the breadth of the ship. All right, and also it will be the breadth of the compartment because the breadth of the compartment is the same as the breadth of the ship. And then the forwardmost compartment is somewhere here, and the length of this compartment is 15 meters. Am I right? Yes. All right, so I'm not to scale, but as best as I can. And then let's fill this compartment with some cargo. So there is some cargo here, and the permeability of this compartment is given as 25. So if you don't know what permeability is the ratio. So once the water starts to come into the compartment, permeability is the ratio of the total volume of the compartment to the volume of water it can hold, considering there is a lot of cargo in there. All right, so the draft is at 7 meters. This is the water line 1 before bilging. So draft is 7 meters. So as soon as it starts to bilge, some water will go into this compartment, right? But because of the cargo spaces, the most of the space is taken by the cargo. So the total ratio is the amount of water that can go into the compartment with the cargo to the total amount of total volume. So that's why permeability, when you see permeability is 25, you will always present it as a ratio. So you divide it by 100 and you use this value 0.25 for your question, or your as a number in the question. I'll show you later on. All right, so this is the situation, and let's now mark some of the important bits and pieces here. So we have the original center of gravity, center of buoyancy, and center of flotation all will be in one line. So now when it's a box shaped vessel and it's even keel, remember that I'm not confusing you. When it's a box shaped vessel and it's even keel, your center of gravity, center of buoyancy, and center of flotation all will be in one line. All right, so I can say G here, B here, all right, F here, they all will be in one line. But as soon as bilging will take place, water will freely float in and out of the compartment, So center of gravity will remain the same, but center of buoyancy will change, and so will the center of flotation. Now in box shaped vessels, since the intact underwater volume will be rectangular, the new center of flotation and new center of buoyancy will remain the same on changing. So let's draw it and show you rather than me talking about it. So I just want to make sure that doesn't get too cluttered. So I will draw the same box shaped vessel now again, and something like this. All right, and what will happen now is that my midship line is still going through the center, let's say, right, and the center of gravity still remains the same. However, because the new water level after bilging, W2L2, this is the new water level, right, so the center of gravity still remains where it is, but the center of flotation and center of buoyancy will now change. So for all purposes, center of flotation will be F1 here, let's call it F1 if this was F, and center of buoyancy will also be, let's call it B1, and say this was B or something like that, right? So it will change, but new center of flotation and buoyancy will be the same. So if you don't know what flotation and buoyancy is, center of buoyancy is the longitudinal center of buoyancy we are talking about here, and longitudinal center of buoyancy or the center of buoyancy, so let's say this is aft and this is forward. So we are going to talk about longitudinal center of buoyancy, longitudinal center of flotation, and longitudinal center of gravity, because this is we are talking about trim here, and everything is with respect to aft perpendicular or longitudinal distances. So center of buoyancy is of course the centroid of the underwater volume, and center of flotation is the centroid of the intact water plane. So in this case it's a box shaped vessel, and in this case the new center of flotation F1 will be in line with the new center of buoyancy B1, although the center of gravity will not change because no weight is getting added, water is freely flowing in and out of the compartment. Alright, so then I will show you some other distances as well as we go along, so that you guys don't get confused. I don't want to throw in too much information altogether. So let's calculate the new center of buoyancy or new center of flotation. As I said, they will be in one line because it's a box shaped vessel, right, and the intact underwater volume is rectangular. So how can I find out the new center? So if there was no cargo, no permeability involved, as you would have seen in example 1, the new center of flotation is the center of the intact water plane area. But in this case, because there is cargo and permeability involved, we will use a certain formula to find out the new center of flotation. Alright, so what is the new formula? Length and breadth of the vessel multiplied by the original center of flotation or longitudinal center of flotation AF. So the original center of flotation was located at midships, so AF was 75 meters, right? That's why I said I'll show you the distances as we go along. And then this is the longitudinal, or this is the length and breadth of the compartment, the forward compartment, multiplied by permeability denoted by the letter P, and multiplied by the distance AF. Now what is AF? AF is center of this compartment here. We'll call it a small f, so that there are not too many f's. The center of flotation is capital F, but the center of the compartment is the small f. Alright, so when I say AF, I mean this distance here from aft perpendicular to this distance here. So this total length is 150 meters, and I will remove 7.5 meters from here. This is 7.5 meters because I only want to measure up to the center of the compartment. So I get 150 minus 7.5. So this is nothing but 150 meters total length minus 7.5 meters, which is 142.5 meters is what I'll be using here, divided by again length and breadth of the vessel minus length breadth by permeability of the compartment. If there is no permeability, then we of course ignore permeability in this formula. Alright, So put the values there, 150 by 20 by 75 minus, you know the values and how I got it. Once I solve the equation, I will get the new center of flotation AF1 or AB1 I can say as 73.27 meters. Right? Now once I have found that out, I know that this is 73.27 meters. Not to scale, of course, it's not to scale, but you get the idea. Right, so the reason I show this much distance is so that it's clear to you. If I make it very close, then it will get very cluttered. All right, so 73.27 should ideally be very close to the midship here, but the reason I'm showing you like this is so that you can understand it better about the difference in distances. So 73.27, and then you can ask yourself how much has the new center of buoyancy been displaced from the center of gravity, or the displacement of the center of rotation from the original value, or the distance of center of buoyancy from the original value. How much is that? So initially gravity, flotation and buoyancy were all located midships in the center, but now it's been displaced. So this distance here, how much is that? That is nothing but 75 minus 73.27, 1.73 meters. And the final distance you have to know, and we can call it D as well, is distance from new center of rotation to the center of the compartment. So distance from new center of rotation to the center of the compartment, this we can call distance D, and you can of course measure it because you know the total length is 150. This is 7.5 meters. You can deduct it and then also deduct 73.27, and you will get 69.23 meters. All right, because you know the rest of the distances, I'm not explaining this. I'm sure you can find your way out to find the distance from F1 to F. All right, we call this F, small f. All right, then we calculate what we call is mean sinkage. Mean sinkage formula is permeability multiplied by underwater volume of the compartment only, divided by water plane area, the original water plane area, minus permeability multiplied by area of compartment. All right, so permeability is of course included everywhere. So permeability multiplied by length of the compartment, breadth of the compartment and draft. This will give me the underwater volume of the compartment. Then original length by breadth of the vessel, and minus permeability multiplied by length and breadth of compartment. I get mean sinkage is 0.179. Now what is mean sinkage? That means when water starts to flow into the compartment here, overall the vessel will sink a little bit because of the water flowing in and out. How much is this sinkage? It's 0.179 meters, and that's why we use the area of the compartment to get an idea of what the mean sinkage will be. So overall the vessel will sink by 0.179 meters because of the water flowing in and out. But how much will the individual drafts change forward and aft is something we'll find out later. All right, so what will be the draft? Initial draft was 7 meters we started out with forward and aft, but overall sinkage will be 0.179 meters. So we will add this to the drafts forward and aft of 7 meters, and we get draft after sinkage as 7.179 meters. Draft after sinkage. All right, now we have to find out how much has the trim occurred, how much trim has occurred, because water has been flowing in and out in the forward part of the compartment, and center of gravity is now forward of the center of buoyancy, new center of buoyancy. So vessel will definitely trim by head because the center of gravity is forward of center of buoyancy. So how to find that out? Let's find out MCTC, moment to change the trim by a centimeter. How much is that? So the formula is displacement denoted by capital letter W multiplied by longitudinal GM divided by 100 times length between perpendicular of the vessel. In this case, it's the length of the vessel. So since kg is not given in the question, if you see example 1, we had kg given there, so we found out longitudinal gm. We will calculate, or we will consider gm longitudinal equal to bm longitudinal. All right, so bm longitudinal is calculated by the formula I by v, where I is the moment of inertia and v is the underwater volume of the vessel. So if it was bm transverse, the formula would have been lb cube by 12. L is the length of the vessel, b is the breadth of the vessel, but this is longitudinal moment or longitudinal bm. Formula becomes bl cube by 12, opposite. So bm longitudinal is bl cube by 12, or 12v rather. V is the underwater volume. That goes without saying. All right, because we have the volume there, so you know. All right, so let's start. So what do we mean by I, or moment of inertia? Moment of inertia, here we want moment of inertia of the intact water plane that has not been affected by bilging. And of course, V is the original underwater volume that is established. So we can keep that aside. Underwater volume is simple, right? Length by breadth by draft. Original length by breadth by draft of the vessel. So we keep that aside. We know how to do that. But let's find out how to find out moment of inertia of intact water plane. So moment of inertia of intact water plane would be easy to find out if I find out the moment of inertia of the total vessel and subtract moment of inertia of the lost water plane, that is of the compartment. That will give me the intact water plane. So intact water plane is the length of the vessel which is behind the compartment, which has not been affected by bilging. All right. So I total, or moment of inertia total, is bl cube by 12. V is anyway at the denominator, so we don't include V in this formula, or the underwater volume. And I total will be bl cube by 12 plus length by breadth of the vessel multiplied by this moment that has been created due to the shift of the center of buoyancy. Square of that. All right, BB1, something that we have found out already here, BB1. That's why we found out the distance. All right, because we are trying to find out the new moment of inertia based on the center of buoyancy, shift of center of buoyancy. And moment of inertia of lost water plane, very similar, bl cube by 12. This is of the compartment, this is the compartment, and this is the vessel. Multiplied by, because permeability is there, plus length by breadth by permeability, multiplied by the F1F square, the distance from the new center of rotation to the center of compartment. Very easy for you to remember. All right, one is with respect to the shift in the center of buoyancy, because that is with respect to the vessel, and one is with respect to the compartment. New shift, new center of rotation to center of the compartment, or you can say new center of buoyancy to center of compartment, either or, whichever works for you. So then just put in the values. You know the values already. All right, we have found out BB1, we have found out F1F, or we can say B1F, whatever you want to call it. You can find out, right? So you know the values already. Don't get confused. This is either or. Okay, so don't think I'm saying divided by. All right, so you can use either or value. So I total, just put in the values here and find out what is I total, and then I lost, put in the values and find out what is the value here, and then put it in the overall formula of longitudinal BM. So this is I total. Oh, sorry. So there is some mistake here. So this should be, yeah, sorry guys. So I had to make some changes because I think I wrote addition instead of subtraction. So I've corrected those changes now. So longitudinal BM is I total minus I of a lost water plane. So you'll just put these values here, the ones that you have individually found out, and then divided by the original underwater volume. So length of the vessel by breadth of the vessel by draft, and you will get the longitudinal BM value 251.10 meters. Then put it in the formula of MCTC, where W is the displacement multiplied by GML, which you will replace with longitudinal BM now. If you have kg available, then of course you can find out longitudinal GM. but displacement is length by breadth of the vessel by draft of the vessel by density. This is the displacement of the vessel multiplied by longitudinal BM divided by 100 is a constant, and L is the length between perpendicular or the original length of the vessel, and you will get MCTC as 3600.33 ton meter. Moment to change trim by 1 centimeter, or moment to change trim by ton per meter. I think it is ton per meter or ton per centimeter, whatever you want to call it as. All right, so it's up to you depending on the unit you have chosen. All right, now you have MCTC. You can find out the total change in trim. So total change in trim is equal to trimming moment divided by MCTC. What is trimming moment? Trimming moment is the weight of the water which has been flowing in and out multiplied by the trimming moment that has been created by the distance. So I will show you what it is, divided by MCTC. So weight of the water which has been flowing in and out is the total length of the compartment by breadth of the compartment by draft of the compartment multiplied by permeability and density of the water in which it is floating, multiplied by D. D is the same distance as capital F1F. All right, so D is this distance here. I've shown you this distance. It's the same as F1F that we calculated here, 69.23 meters. All right, so you'll just put that distance here because that's the trimming moment from the center of the compartment. So this is D, and you get 103.4 centimeters. You can round it off to 103 centimeters if you want, and then convert 103 centimeters to meter, because you'll have to apply this total change in trim to the drafts which are in meters. So just divide 103 by 100 and you will get the value 1.03 meters. This is in meters, of course. All right, so this is total change in trim. So what is the change in trim forward? Change in trim forward, the formula is total change in trim multiplied by LBP, or length between perpendicular, minus the new center of rotation, longitudinal center of rotation, LCF1, divided by LBP, length between perpendiculars. So 1.03 is the total change in trim multiplied by LBP minus LCF1, which we found out earlier, divided by LBP is 0.53 meters. And then to find change in trim aft is total change in trim minus TF. You will get 0.50 meters. So your drafts after sinkage or applying sinkage, so we applied sinkage earlier, remember, 7 meters, and we added 0.179 of sinkage over here. Just to show you again, where was it? Here, right? Drafts forward and aft, and after sinkage is 7.179 meters. Some people apply sinkage at the end, some people apply at the beginning. I leave it to you what you want to do. It's the same thing. And then because new center of buoyancy is aft of gravity, you will add the forward trim and subtract the aft trim. So you add the forward trim to the forward draft, you get final draft 7.706, and subtract the aft trim, you get 6.679 meters. So if the center of buoyancy, new center of buoyancy, was forward of center of gravity, then you would have done the opposite. You would have subtracted the forward trim and added the aft trim. So in another example I will take in future, I will do that. I will take a probably situation where there is a bilging in the aftermost compartment. So guys, let me know what you thought about this video. The reason I'm taking a lot of these topics, or I'll take a few examples, because it's a difficult topic to understand. It's complicated and students often ask me questions about this. So I'll be putting up lots of examples so that you can understand what exactly is going on. Please watch all examples so that you have a good understanding of this topic. Thank you.